Let's take a look at the last example. Here we have example 5. We consider the function g of x is equal to 5 divided by x to the third. We're going to calculate g of 2 and also the derivative of g of 2. And we're going to use it to approximate g of 2.1, g of 1.95, g of 1.99, all with differentials. We start with understanding that g of x, which is 5 over x to the third, can be rewritten as 5 times x to the minus 3. I rewrite it that way so that it's easier to take a derivative. The derivative becomes negative 15 x to the negative 4th, which, if you'd like to rewrite again in fraction form, is going to be negative 15 divided by x to the positive 4th. So whether you're more comfortable dealing with negative exponents or positive exponents, either way is okay. In terms of what we get when we plug in 2, if I plug in 2 to the function, I would get 5 divided by 2 to the third, or 5 times x to the negative 3, which is simply 5 over 8. Now, I'm going to utilize decimals to do my approximation, but you could use fractions if you want. So I'm going to write 5 over 8 as 0.625 while doing my approximations. Similarly, the derivative of g evaluated at 2 is negative 15 over 2 to the 4th. Now, 2 to the 4th is 16, so negative 15 over 16 is negative 0.9375. Now we are ready to approximate. Let's approximate g of 2.1 using differentials. We take g of 2 plus g prime at 2 multiplied times the differential dx. Actually, let me once again use the approximate symbol. So g of 2.1 is approximately equal to 0.625 plus negative 0.9375 multiplied times the change in x. Now, from 2 to 2.1, the change in x is a 0.1. We can calculate that. 0.625 minus 0.9375 times 0.1 gives out a value of 0.53125. Depending on how far Moodle asks you to round it, depends on how you write your answer. But that is the approximation rounded to 5 decimal places. Now, if we want to approximate the other values, like 1.95 and 1.99, we do those in the same way. G of 1.95 is approximately equal to g of 2 plus g prime of 2 multiplied times dx. In this case, g of 1.95 would be approximately equal to g of 2, 0.625. The derivative of g at 2 is negative 0.9375. And the differential here, because we're lower than 2 by 0.05, we have to use negative 0.05. When I plug that into my calculator, I get a positive 0.671875. Again, if Moodle asks you to round to 2 decimal places, go ahead and round that number to 2. If Moodle asks you to round to 4, round to 4. The last approximation we were asked to do was G of 1.99. Again, we're going to start out with G of 2 plus G prime at 2 times the differential dx. And G of 1.99 becomes 0.625 minus 0.9375 multiplied by a change in x of 0.01. Actually, I'm sorry, negative 0.01. We went down by 0.01. And that means the approximation for G of 1.99 is about 0.634375. Once again, this is an approximation. If you want to look at how good the calculator gives you an answer, so this was an approximation. I probably should have used the approximation symbol. The calculator, when I plug in 1.99, I would plug that into 5 divided by 1.99 cubed. And so G of 1.99 becomes 0.6344695,372. Again, that's pretty close to what I'm getting. You can see in this section that the differentials often give you very close numbers to what the actual function values are. And again, in a situation where I don't have a calculator handy that can take 1.99 to the third power or sine of 0.01, this becomes a really good tool. This also becomes a really good tool when we don't have well-defined functions. So when our functions aren't algebraically defined, but we have some sort of a graph for them. We've seen how that kind of works in earlier sections too. This shows you that differentials can approximate the function values at values close to what we already know.